We're surrounded by this invisible force all the time, thermal energy. It's why that first sip of coffee on a cold morning feels so amazing, or why a cool breeze is just a gift in the summer. But how does all of that actually work? Well, in this explainer, we're going to break down the physics that keeps us comfortable, from what's happening on your stove to the ground right under your feet.
So, let's start with a puzzle you've probably run into in your own kitchen. Why does it take what feels like an eternity to boil a pot of water for soup, but you turn your back for 2 seconds and the oil in a frying pan is sizzling hot? It's not magic, I promise. It's pure physics. And the answer reveals this really cool hidden property inside pretty much every substance.
The key to that whole kitchen mystery is something I like to call a material's thermal stubbornness. It's the reason a metal spoon you leave in your soup gets scorching hot almost instantly, while the soup itself takes its sweet time to warm up.
Now, the official scientific name for this stubbornness is specific heat capacity. It sounds a little intimidating, but the idea is actually super simple. It's just the amount of energy you need to pump into 1 kilogram of a substance to raise its temperature by just 1 degree Celsius. So, a high value means it's really stubborn. It fights against changing temperature.
Take water, for instance. Its specific heat capacity is a whopping 4,180. That means water is basically a thermal sponge. It can soak up a massive amount of heat energy before its temperature actually starts to climb. And that is why your pot of water takes so long to boil.
Okay, now let's look at copper, which is what a lot of good pots and pans are made of. Its specific heat is just 380. That's more than 10 times lower than water. It takes barely any energy to get it hot, which is why the pan heats up in a flash and why a metal spoon can burn you so fast. It's got almost no thermal stubbornness at all.
So how do we actually calculate all this? Well, scientists have a handy little formula. Q equals mc delta T. Now don't let the letters scare you. It's not really a scary equation. It's more like a recipe for heat. It tells you the exact amount of energy, that's Q, that you'll need to get a specific change in temperature. And here's how that recipe breaks down. First, you start with the mass of whatever you're heating up, that's M. Then you multiply that by its thermal stubbornness, the specific heat, which is C. And finally, you multiply that by how much you want the temperature to change, delta T. It's that simple, and this little recipe governs everything from boiling an egg to understanding global climate patterns.
All right, let's zoom out of the kitchen for a minute, because these same principles don't just cook our food. They literally build the world around us. They shape the cities we live in.
This brings us to a huge concept called thermal expansion. When you heat something up, its tiny little particles start vibrating faster, and they spread out, making the whole object get bigger or expand. And the opposite happens when it gets cold. It shrinks or contracts. This simple push and pull of molecules has massive consequences for our infrastructure.
And you see this principle in action everywhere, even if you don't realize it. You know those metal joints on bridges or the little gaps in sidewalks? Those aren't mistakes. They are absolutely essential. They give the concrete and steel room to expand in the blistering summer heat. Without them, bridges would buckle and our sidewalks would shatter. It's a perfect example of physics keeping our world from falling apart.
So, we see how heat and cold literally shape the world outside. But what about when we want to take control? That brings us to the incredible engineering that keeps us comfortable inside our homes, no matter if it's freezing cold or boiling hot outside.
A typical furnace is a great example. It's actually a pretty simple system. It just heats up air, and because hot air is less dense, it naturally wants to rise. The furnace just gives it a push through a series of ducts into your rooms. As that air cools down, it gets pulled back to the furnace to get reheated. It's just one big, continuous loop designed to keep you cozy. But what about cooling? Okay, this is where it gets really clever. Your air conditioner or your fridge doesn't actually create cold. That's a huge misconception. It's really more of a heat magician. Its whole job is to perform a trick. It grabs the thermal energy from inside your house and just dumps it outside. So how does this magic trick actually work? Well, it's a 4-step cycle that just repeats over and over. First, a special gas called a refrigerant gets squeezed, or compressed, which makes it super hot. Second, that hot gas travels outside, where it releases all its heat and condenses into a liquid. Third, that liquid is forced through a tiny valve, the pressure plummets, and it becomes intensely cold. And finally, that super cold liquid flows back inside, where it absorbs the heat from your room's air. That absorption turns it back into a gas, and the whole cycle starts all over again. It's just a constant loop of moving heat from inside to out.
But let's be honest, those conventional systems use a lot of energy. So what if we could tap into a much more sustainable source of thermal energy?
What if we could just use the Earth itself?
And that is the big idea behind a geothermal system. See, just a few feet below the surface, the ground stays at a remarkably stable temperature all year long. A geothermal system uses a network of underground pipes, kind of like a radiator, to tap into that stable temperature.
The real genius here is that it works both ways. In the winter, when the ground is warmer than the air, the system pulls that heat out of the earth and pumps it into your house. But then in the summer, it completely reverses. It pulls the heat out of your house and dumps it into the cooler ground. It's a heater and a super efficient air conditioner all in one.
Of course, it's not a perfect silver bullet just yet. There are definitely trade-offs. On the plus side, geothermal systems have really low running costs, and they don't burn any fossil fuels, which is a huge win for the environment. The big downside, though, is the upfront installation cost can be pretty significant. And there's always a small risk of the fluids in the pipes leaking.
So, from the water in your kettle to the sidewalk outside to the very ground under your home, the physics of thermal energy is just everywhere. It really makes you think, right? We are living on a giant battery of thermal energy. So the question is, what's the next amazing way we're going to learn how to use it?